Hello everyone, welcome to EGN 3343 Thermodynamics, and today we are going to look at a review for exam number 1. Basically, we are going to talk about the format for the exam. We are going to be also talking about the structure of the exam, the duration, and where it's going to be available, and we are going to actually list the content and specify exactly what you should expect for exam number 1. So exam number 1 will be available online at DSC at the time, that's D2L or Florida Online. The times are already pre-scheduled in the calendar for the semester, and on the Florida Online calendar as well, you will see when the exam is going to be available. The exam is available for a window of about 3-day window. And during that 3-day window, you have 120 minutes to take the exam. So once you open the exam link, you have about 120 minutes, a maximum of 120 minutes to complete the exam. The exam is electronic and it's online, so you are to complete, scan, and submit electronically as PDF through the Dropbox. Because there's a scan process and a submission process involved, I will give a 10 to 15 minute grace period. So if you're past your 120 minute allowance, you can you're safe, because there's a grace period for the scanning and submission process. You may also complete here at the ATC. If you're around, you can come to the atrium or the main engineering technology office and take the exam here, but you have to log the times with anybody who's available around. If it's me or any other secretaries or any of the other faculty, they can log the time of start and the finish time on the test. The exam is open books and open notes. All the solutions to the assignments will be available online, and the use of computers and programmable calculators is allowed. It's very important that you have access to thermodynamic tables, because you're going to be using them during the test. The topics that we are going to be covering on the test are basically the topics from lecture number 1 to lecture number 8, which are concepts and definitions, properties, states, and processes, the conservation of energy, leading to the first law of thermodynamics for closed systems, expansion and contraction work, pure substances, the first law applications for pure substances, and the first law applications for ideal gases. So essentially, the test is a combination of the problems that we had in assignment number 1 and assignment number 2. We had 5 problems in assignment 1, 5 problems in assignment number 2. And I can advance you right now that you should expect 2 problems for exam number 1. One of the problems is going to be on pure substances, and the first law applications of pure substances, where you're going to have 1 or 2 processes on a pure substance. That's either water, or refrigerant, ammonia, whatever one of we have available on the tables. And problem number 2 is going to be first law applications on an ideal gas: air, nitrogen, CO2, so on and so forth. And so you're going to have 1 or 2 processes acting upon an ideal gas. So the properties, we define them or classify them as intensive and extensive. The intensive properties are temperature and pressure. Temperature can be measured in degree Celsius, that is the relative SI scale, SI, the international system, or Kelvin, which is the absolute scale to the Celsius scale. So to obtain a temperature in Kelvin, you have to add 273 to the temperature in Celsius. The pressure P is also an intensive property. That means that it doesn't have to do with the size of the system. You cannot define a specific version of an intensive property. The pressure is measured either in bar or in kilopascals in the SI system. Remember, 1 bar is 10 to the 5 pascals, or basically 10 to the 2, 100 kilopascals. 1 bar is equal to 100 kilopascals. Then you have 3 extensive properties. We're going to add another one in the lectures that follow up exam number 2, but for now we are dealing with volume, internal energy, which is measured in kilojoules in the SI system, and enthalpy, which is also measured in kilojoules. Remember that the enthalpy is simply the energy plus P times V. That's defined like that, and we went over that explanation during the lectures. There are specific properties which are specific to every one of these every extensive property has a specific version. Specific version of an extensive property is basically the property divided by the mass of the system. So the specific volume is basically the volume divided by the mass. The specific internal energy is the internal energy divided by the mass, and that is relevant here in the units. The specific enthalpy is the enthalpy divided by the mass. Then we defined the types of thermodynamics. Once we define the properties compose a state of a thermodynamic system. So basically a state of a thermodynamic system is composed by the interaction of these 5 properties: temperature, pressure, volume, energy, and enthalpy. So by assigning a value to each of these properties, you can define the state of a thermodynamic system. Then we talked about a process or processes. Thermodynamic processes are those energy interactions that will take you from one state to another state. There are 2 kinds of processes that we're going to study in this class: heat processes and work processes. Heat, which we define by letter Q and is measured in kilojoules because it's a form of energy, is energy transfer due to a temperature difference between the system and the surroundings. And I repeat this many times: heat is not temperature. Okay? Temperature is a property of a state. The temperature of this room has a number. The temperature of this room can have a different number at some other point in time. Heat is a transient form of energy. You add heat to this room to change the properties from one state to another. It doesn't necessarily mean that by adding heat you will be increasing the temperature, or by removing heat you will be decreasing the temperature. There might be other interactions of the properties that perhaps make the temperature stay constant or decrease when you're adding heat. The other form of process is the work, is another form of transient energy, also measured in kilojoules. Is energy transfer due to a potential difference other than temperature. It is done by a system if the sole effect external to the system could have been the raising of a weight. So this, from the mechanical point of view, is defined as the raising of a weight over a distance. The first law of thermodynamics for closed systems can be summarized as the change of energy, change of internal energy U from one state to another state, so that's U2 minus U1, is equal to the amount of heat added to the system minus the amount of work done by the system. And listen closely to what I'm saying. The amount of heat added to the system minus the amount of work done by the system. That means that heat added to the system is positive and heat removed from the system is negative. When I talk about work, that means the work done by the system is positive and done on the system is negative. Now, internal energy U is one specific component of the total amount of energy content of a system, where energy can be a content of internal energy, that's molecular interaction or composition, kinetic energy, potential energy, and all other forms of energy. But for closed systems, we are going to neglect changes in kinetic energy, potential energy, and all other forms of energy, and we are going to just basically say that the first law of thermodynamics resumes to, or summarizes to, change in internal energy is equal to Q minus W. The work on this equation, on the first law of thermo, can actually be calculated. The heat cannot be calculated other than just calculating it from this equation, because the process for calculating heat transfer is beyond the scope of this class. Heat transfer can be obtained from the mechanisms of conduction, convection, radiation, or the combination of these, but that's beyond the scope of this class. So heat can either be zero when you have an adiabatic process or an insulated system, can be given as a quantity, the amount of heat dissipation or the amount of heat added to a system, or it can be the unknown to actually calculate directly from the first law of thermo. Work, on the other hand, is something that we can calculate externally. We can calculate by some constitutive relationship, and that relationship, from the definition of work, has to do with the change, with a force over a distance, which can actually be expressed in terms of a thermodynamic quantity called pressure and volume. Basically, if you say that work is equal to force over a distance, you divide the force by the area and multiply the distance by the area, and then you can say that the work is equal to the pressure times the change in volume. That's why this reduces to an integral representation. Work in a closed system is equal to the integral between V1 and V2 of the pressure. Okay, so it's basically the pressure added over a change of volume. If the volume doesn't change, as you can see, this integral leads to 0. If the change of volume is positive, that means expansion, this integral is positive. If the change of volume is negative, that means, or contraction, that means that this formula leads to a negative value of work. So work for an isometric process, 0, expansion process, positive, contraction process, negative. And that's summarized here. In isometric processes, that means that delta V is going to be equal to 0. The change of volume is equal to 0 between process 1 and process 2, or state 1 and state 2. That leads to 0 work. When the process is isobaric, that means that the pressure doesn't change throughout the process from state 2 to state 1, delta P equals 0. The work, that pressure comes out of the integral, and the work is simply pressure times V2 minus V1. If we have a linear process, that means that the pressure changes linearly with volume, meaning it's a straight line, that if you can plot it in a PV diagram, you actually get a perfectly straight line. Then you can calculate the area under the curve, because this integral is nothing but the area under the curve in the PV diagram. That the area under the curve is the area of a trapezoid, where the x-axis contains the volume and the y-axis contains the pressure. And for polytropic processes, those processes that follow the curve, P times V to the power of n equals to a constant. These are the so-called group of polytropic processes. That integral resolves to the following. If n is greater than 1, then the work is P2V2 minus P1V1 divided by 1 over n, or 1 minus n. If n is equal to 1, this W resolves to P1V1 times the log of V2 over V1, or simply P2V2 times the log of V2 over V1. Same thing, because P1 and V1 are equal to P2 and V2 when n is equal to 1. The state postulate for a simple system states that only two independent properties are needed to completely define the state of a thermodynamics, or of a simple thermodynamic system. That means that if we have two properties, we can somehow, through constitutive relationships, find the other three or the other four, or as many properties define a state. So if we had temperature and pressure, that means that we technically can know the complete state. If we have temperature and volume, or volume and pressure, or energy and pressure, or enthalpy and volume, and so forth, so on and so forth, whatever number of combinations we can have. Knowing two means that you can potentially know the rest. Now, we use the state postulate to assign specific meaning to these systems, thermodynamic systems, and we started by looking at pure substances. What happens if a thermodynamic system is composed of a pure substance? A pure substance is usually homogeneous in nature, and is a substance is a fluid that is bound to change phase under normal operating conditions. And the examples that we use in this class, or for which we have tables, are water, refrigerant 22, refrigerant 134A, ammonia, and propane. Now we use the tables to relate the properties: temperature, pressure, volume, energy, and enthalpy. And remember the state postulate: if you have two, that means you can know the rest. So normally these tables are organized in a way where, knowing two properties, you can know the other three. The first thing you need to do is determine the substance you're working with, and then determine the fluid condition. Find out through the tables whether the substance is on compressed liquid region, is liquid, whether it is saturated liquid, that is liquid that's about to boil, to start boiling. C, whether it is wet vapor, that is a combination of liquid and vapor, so it's a substance that is currently boiling, so it has some component of liquid and some component of vapor, a fraction of each. D, saturated vapor. This is a substance that completed boiling, but it just completed boiling. The last set of liquid drops actually boiled. And superheated vapor, this is a substance that's to the right of the boiling phase, meaning that it completely boiled and now its properties have been increased and is far away from the boiling phase. Now, if substance is on saturation phase, that means B, C, or D, either saturated liquid, wet vapor, or saturated vapor, pressure and temperature are no longer independent of each other. If you don't change the temperature, the pressure is not going to change, and vice versa. So therefore, the state postulate doesn't apply anymore because P and T are not independent of each other. That means that you need another property. You need to define another property. When you are inside the saturation region where the substance is boiling, currently boiling, you define this property called quality X, and you define as the proportion of vapor mass to total mass. Remember, on this region, B, C, or D, there, especially on C, the wet vapor region, there is a fraction of the substance that is liquid and a fraction of the substance that is vapor or gas. We call that gas G and fluid F. So you define this mass proportion X as the mass of the gas divided by the total mass, and then you can use it to relate the other properties. X, or the quality of the state, is equal to the if we're talking about volume, for example, is the volume of the property, or the volume of the system, the specific volume of the property in the system, of the substance in the system, minus the volume of the saturated liquid divided by the volume of the saturated vapor minus the volume of the saturated liquid. And you can use this relationship for energy and enthalpy as well. So this will help you actually calculate the value of a property, for example the volume or the energy or the enthalpy, based on knowing the quality and knowing what properties would the saturated liquid or the saturated vapor would have. Ideal gases is the second type of substances or second type of systems that we analyzed. These are also substances, but these are substances that exist only in the vapor form, far from its saturation zone when it is under normal operating conditions. So these are elements or compounds or substances that normally exist in gas form, in vapor form. The examples that we use, for which we have tables, are air, hydrogen, oxygen, nitrogen, CO2, and CO. That doesn't mean that these substances or ideal gases cannot be condensated, cannot be actually liquefied. They could, but you need to actually impose them to very extreme conditions of pressure and temperature in order to do that. So under regular operating conditions, they exist only in gas form. When that's the case, a very simple state equation relates pressure, volume, and temperature, the three fundamental thermodynamic properties. So we no longer have to rely on tables to be able to determine temperature from pressure or volume from pressure and temperature, or pressure from temperature and volume. Because the relationship P times V divided by T always remains constant at state 1, at state 2, at state 3, and anywhere in between. So the equation of state for an ideal gas, that constant proportionality, is called R. R is the gas constant. It's a constant that depends on the specific gas that you're working with. P times V is equal to RT. If you make the specific volume V equals to the absolute volume divided by the mass, then P times V is equal to MRT. You can also define, or R, the gas constant, is defined as the universal gas constant divided by the molecular mass or the molecular weight, M. And N, which is the molar number, or the number of moles in a system, is equal to the mass of the system divided by the molecular weight. So these equations of state can be expressed in molar form as P times V, total volume, equals to nRUT. And this state equation is universal regardless or independent of the number of the type of ideal gas or of the ideal gas that you're working with. So whether this is air, oxygen, nitrogen, CO2, CO, whatever it is, this particular equation applies as long as you know the number of moles in the system. Otherwise, if you know the substance, if you know the ideal gas, this is the equation that applies. Now, that equation of state is used to relate the pressure, volume, and temperature, which are called the three fundamental thermodynamic properties. Now, how do we relate the energy back to these properties and the enthalpy back to these properties? For the case of pure substances, we went to tables. For the case of ideal gases, there's a relationship for it, also a constitutive relationship, which is an integral from over a range of temperatures of something called the specific heat at constant volume, that's for the energy, and for the enthalpy is the integral over a range of temperature of the specific heat at constant pressure called Cp. Under certain circumstances, the Cv and the Cp can actually be considered to be constant, and then therefore the change of energy can be related directly to the change of temperature as Cv times delta T, and the change of enthalpy can be related to the change of temperature as Cp times delta T. In ideal gases, the change in energy only depends on temperature, and enthalpy only depends on temperature. That's for ideal gases. Now, if we cannot make the assumption that Cv and Cp are constant over these range of temperatures, then we rely on tables, on thermodynamic tables, and we solved problems using those tables. And in that case, we go to the table with the temperature and obtain a value for U, and go to the temperature with the other temperature, obtain a value for U, and then we can calculate the change in internal energy, and we can do so exactly the same way for the enthalpy as well. The relationship of these specific heats, a constant pressure and a constant volume, is such that the gas constant R is equal to Cp minus Cv, and this quantity, or this ratio called K, is called the isentropic ratio, or the ratio of specific heats, is simply the ratio of Cp over Cv. So this is the type of, this is the material that you will be needing to work on exam number 1. Remember that exam number 1 is going to concentrate on the application of the first law for closed systems. You're going to see 2 problems, one applied to a pure substance like water. There's a couple of processes involved to take the water from one state to another, and then from that state to another state. And then you're going to see another problem where there's going to be an ideal gas, such as air, in which there are going to be some processes that will take the air from one state to another, and then from that state to another state. And that's going to be exam number 1. Very similar to some of the problems in the assignment. So good luck on exam number 1. Thank you very much for your attention, and I'll see you on the lectures after exam number 1. Goodbye.